Hi everybody. Well, today let's continue with lecture 11. And in lecture 11, we will discuss the so-called advanced assembly programming techniques. Those are the issues covered in chapter 3. And so we already have a background about how to write a simple program, and we already have some building blocks for programming. So in chapter 3, we will discuss some advanced the programming techniques. So we will revisit the assembly process. And this is the issue covered in section 3.1. Yeah, 3.1. And I think you guys already have an idea. And then we will discuss the loops and stacks. Loops, that are the issues covered in section 3.2 and 3.3. And I think we already have some ideas about loops and stacks, but in this lecture, we will have detailed discussion about that. Then, and if you have time, we go to the issue of subroutines. So subroutine is the topic covered in section 3.4. And we will continue with the issues of subroutine in lecture 12. All those issues, they are like in high-level programming issues. So let's start with sampling process. And as I'm pretty sure you guys already have an idea about the assembly process. So assembly process is what? Is to convert, the assembly language source program into the machine code. So the CPU can understand that. So the key component, is assembler. And we have long discussion about assembler. So assembler does a job. So assembler reads each instruction that a programmer wrote and convert it into strings of 0 and 1s that we simply call the machine code. We call the machine code. This machine code interpreted by CPU. So the source program, so the original program written by a programmer, we simply call the source program. We call the what? We call the source program. Is in the format of .asm assembly .asm. Then so original source program is converted by assembly into 0 and 1s. Then after we convert it into machine code, or we call it machine language. This file format has extension .s19. So we have conversion issue from this. Source program and machine language. In addition to strings of 0 and 1, so in addition to 1 and 0, the S19 file, that's the machine code, also contains some overhead bits. Overhead some bits we simply call the what? Like some control bits. Those bits of the S19 file are used to accurately transfer a machine code file, which is a 0 and 1 file, between the host PC and the 68HC12 microcontroller. And those overhead bits in the S19 file, they are generated by the Motorola's 8-bit object code format. Now here we mention some issue about the host PC and the 68H12. What's this about? We see here we go. This overhead bits what? Something used to what? Used to transfer the machine code between host PC and the 68H12. What does that mean? In general, if we need to program a 68HC12 microcontroller, in general, we connect the microcontroller board to a computer, to a host PC, okay, like a mouse. So we connect the board into host computer. Then we write our program. We do assembly, we write the source program, okay, using on the PC. So we have some communication and transfer of information file between the 68H12, like external device, and the host PC we're programming. So this overhead information used to manually to help to accurately transfer the machine code file between the PC, okay, and the 68H12. So after we do assembly, okay, we have S19 file. This S19 file is used by loader program. Okay, remember if you took a C or C++, we have a load program. Load program is another software program. Okay, we have assembler, we always have loader. Load is the what? Is to send and receive the program file between the PC and the 68H12. Remember we have a source program, we have assembler, we also have a loader, okay, and we also have what? CPU. So let me show you a very simple example, and I'm pretty sure you guys already have some ideas about this, but that's fine. Let me show you again. Let me show you this very simple instruction: LDAA $25. So that's very obvious. This is what? This is LDAA to run in the immediate address mode. The operand is 25 in the hexadecimal. So here, this is very obvious. LDAA runs immediate mode because his operand started with $. Okay. So if LDAA runs in the immediate mode, then what? If you go to appendix, and remember that so I think you guys already still remember very well. Yes, if you turn to page 549, so if you turn to page 549 of the book, and then we can see the instruction LDAA, why it runs in the immediate address mode, is machine code is 86. And if you run some other modes, what is machine code still? If it runs in the directory mode, is machine code 96 and B6 and blah blah like this. So its machine code for LDAA is B6. So if we convert it into the binary, when we convert the B6 into binary, okay, that's obvious. Here we go. So this is 1000 is B, 0110. This one, let me show this way. Use a thinner pen. Show this one B, this one 6 on the 1 byte. Here we have percentage sign represented one. This one is binary. Remember number systems. So this as 1000 and 0110 is a machine code for LDAA, and the rest 1 byte 0010 0101, okay, that corresponds to 5. This is 25, 2, this is 5. They are what? They represent the operand. So as I showed here already, okay, it's very clear here. I show here. Now when CPU see the machine code 1000 0110, okay, CPU knows, okay, is to perform the loader accumulate A task. So the data we load into A will be the next byte, which is 25, which is this 2, which is right here this byte. Excuse me, this byte. So it's so easy. So this is a very simple example to show this assembly process. So here I use a format of chart to show you assembly process. So at the beginning, we have source program. So as I show you here, we have source program here. We have source file, we call it source program, yeah, or we call it source file. Okay, yeah, this is what? This is written by a programmer, okay, by a programmer, or by you, or by me. Okay, it's what? When we save it, it's in the format of .asp. Let's show you. .asp. Then, okay, we do assembly process. We do assembly process here. Okay, by assembler. Okay, so we have machine code. Machine code here is labeled as what? .s19 file. Okay, that's .s19 file. In addition, in addition, we have another file. It's called .lst. This file. So when we do assembly, we have option. So the programmer, or the person running doing assembly process has option to create a .list file. In addition to the default, the S19 file. .s19 file will be used by CPU to execute. And then .lst file is option. It's not run by CPU. It's mainly used for debugging process. So the programmer can check what's going on there, can check to see where something's wrong and what happened with each instruction at what machine code and at what memory location, like this. So here shows us assembly process. So as I said, the list file is optional. It's mainly used for debugging. So then what information is contained inside the list file? It contains address for each instruction. Or we simply say it tells us, at the involved address, what's inside. What's the machine code at each individual memory location. So address and contents of each address and source code. Source code is nothing but what? But the original language program we wrote. So as just you go to page 77 in the book, they give us a very good example and had a very good discussion about that. So this is pretty much the first bullet. We focus on assembly process, which that section covered that's the issue covered in section 3.1. Now let's go to the second topic, the second bullet, loops and stacks. And we start with loops first. That's the issue covered in section 3.2. So if you took a C or C++, I assume you guys already have quite a good understanding about loops. So here I showed us what in the high-level language, what's the main idea of loops. So here I show you like this. For something, here we have I equals 0, I less than or equal to 10, I plus, and do something. This is shows us what in high-level language, a loop is to perform the code iteration. Now, although we didn't have a very good discussion about loops, but we already saw the loops before when we did some lab exercises or when we did some homework problems. So in general, there are five steps involved, to build a loop. Or when we use loop, there are 5 steps involved. Step 1, we have the initialized loop counter. So because when you run a loop, we have to control how many times do you want to run. So that's the job done by loop counter. So we have to initialize a value to the loop counter. Then we specify, when the condition is met, what type of operation do we need to perform. So we have to specify the operation. Do we need to load some data? Do we need to store some data? Or do we need to make some change like this? Then, after this one, we have to increment the loop counter. At the beginning, we initialized right here, but now we have to increment. We have to change the loop counter. Okay, so we can only perform operation for a certain number of times. So we either increment the loop counter or we decrement the loop counter. It depends on what's the initialized loop counter. Then, okay, afterward, after we incremented the loop counter, we have to compare with a threshold, or we call it a limit. We have to compare the counter. Okay, we have to compare the counter here, this counter here, okay, with limit. If we still meet the requirement, or in other words, if we happen to go beyond our limit, then we repeat. Okay, if we reach to our limit, then we have to stop. We have to exit. That's the step. That's the step 4. Okay, probably I should call it right here. This is step 3. This is step 3. Yeah. Then here, let me show you. This is step 4 and 5. This is step 4. This is step 5. Like this. So exit if the value of loop counter here, okay, which we incremented. Loop counter here, we incremented here, or we decrement. So if loop counter is greater than the upper limit. Now if you decrement instead of increment, then what? Then we exit if the value of loop counter is less than the lower limit. Okay, here's limit. So here we do testing. Here we exit or not. It depends on testing result. Now this pretty much shows 5 steps involved. So let me show you a very simple example of loops. This is a very typical example. And this is a very good example shown us on page 79, I think. Yes, this is an example shown on page 79. So let me show you here. This is an example on page 79. This is a very typical example using loops. And here, in order to help you understand, we list all four fields for the instructions. Okay, we see right here we have what? We have label, we have opcode. Opcode is nothing but operation. Okay, and operand also give you comments. Okay, those are comments here. So let me show those are comments for each instruction. So let's start from the first instruction, opcode. Okay, so at the beginning we load a value 1000 as hexadecimal into index register X. This is what? To initialize index register X. Here we go, see? Let me change different color here. Here we go. That means we make X points to 1000 or memory. Then we load the value into B, accumulated B. What do we need to load? What do we load? We load the sum. What's the sum? Sum, I assume, is a label and is defined before. Assume here it will be defined using the data, the directive. Remember we learned about the data directive before. And if you go back to, so I think this data directive is pretty much similar to our. It's very similar to the examples that I show you on page 61. Or if you go to page 60 or 61, and I'll show you some examples for the data directives. like FCB, RMB, FDB, FCC, like this. And this sum, I think it should be one of the, it should be, and I think it's very likely, like FCB we defined before we defined here, we defined somewhere here, we defined ahead of it. So that means what? That means pretty much we already load the value. We already specify, we already initialize the value for SUM. But here make sure, okay, why I said it is it should be the data directive. It should be a label like the one I show you, like the one we have there on page 61. We have example like ABC, FCB 11, 12, 13. I mean, if you turn to page 61. If you turn to page 61, you see we see some examples of data directives. We see FCB is to form a constant byte, and we reserve memory. We also load the value inside. Then we label it. So this label right here, for example, on page 61, the ABC is pretty much similar to the SUM here. Now make sure SUM here we don't have pound sign. Here you see, we don't have pound sign. Here we go. Okay, because SUM is already a label, already a memory. Okay. Now if this SUM is defined using the EQU, if it defined using EQU, then we have to put pound sign. So I think this one is defined using FCB. Is already reserved memory. So for label, if you already reserved the memory, then we don't need a pound sign. But if you use EQU, okay, is never reserved memory. Okay, it only equal something. So we need a pound sign. Here's pretty much maybe defined as FCB somewhere before, like this SUB or FCB somewhere here, a value here we go. So we load the value, okay, that's labeled by SUM, whatever the value it is, into B. Then we load the 0, 0 into accumulated A. Here we go. Okay, this is what this A, okay, is considered to be loop counter. So we initialize loop counter to 0. That means what? When we get loop, okay, when we change the loop counter, we should increment. Okay, we should increment. Okay. Then what should be our limit? How many times should you perform operation? Or at what point you should stop? Okay, that's defined here in next instruction. Okay, it's first instruction inside the loop. So we load the value 0A, which is 10, corresponds to 10 into A. Now I mean, we use this 10 to compare with the value in A. Because A represents loop counter. So we compare the value of inside A, so CMPA. Compare the value of accumulated A with 0.8. 0.8 specifies as limit. So we increment the value of A until then we increment and we compare. Okay, we increment as a part of job inside loop. Every time after we finish the specified operation, we compare the value of A with 0A. If equal, branch. If the value of A has been incremented into equal to 0A, then we branch. The branch if equal, BEQ, branch if equal. If equal, we stop. If equal, here we go. We use what? We use the relative address mode. Stop. Where is stop? Stop goes to here. If equal, we stop. Stop, then what? Then what do we do? Okay, when we stop, okay, we store the value of accumulated B. Store here into memory. Where's memory? Okay, where's memory? Memory is SUM. Because I show you a moment ago right here. S corresponds to here. SUM is considered to be label or memory location where we already initialized the value at the beginning. So if they're equal, that means pretty much we're done. We finished the specified operation inside the loop. Then we store the value of equivalent B into this location, into the memory location labeled by SUM. Now, if not equal yet, branch. So when we compare the A, if not equal to 0 yet, then what? We sequentially increment. We sequentially execute the instruction. We come here. What do? That's the real operation. ADAB, we add something into equivalent B. ADAB. We add what? We added the value x points to. Remember I told you this here we have 0x because this is index address mode. Okay, we added the value into B. What value? We added the value at memory location pointed to by x. Because this is 0. When you add 0 into x is equal to x. It means we added the value x points to. So where does x points to? X points to memory location 100. See, specified here. That means what? For first iteration, we added the value at memory location 100, whatever it is, into B. What's the value of B? B already contains what? The value of SUM. That's nothing but what? But we means what? We added the value x points to into the value at SUM. But here we specified this value using B, not the SUM, because you cannot add a value in memory. See, that's why you load the SUM into B. You cannot perform arithmetic operation on memory. After we added the value into equivalent B, then what happened? Then we increment x, because what? Because our job is to add some numbers in memory together, and we save our result. So now we already finished adding the first value x points to. Now we should increment the value of x, so I in x. This is what? Inherent address mode. So x has been incremented. X is the loop counter here. Okay. Let me write x what? X specifies the value we need to add. We increment it because we hope to add what? Next value, following value. Okay. Increment index register x. We also increment a. Why we increment a? Because what? We only need to specify. We only need to add the 10 numbers. We already finished adding one number. Then we increment the value of a, so we can only add 9 more. So we increment a, here we go. Then we compare a, here we go. Compare a with the 0, 8. Okay. Then what? Okay. After we increment both the x and a, here we go. We branch. Okay. We branch to where? That means what? If a continuous matter, we branch to check. BRS branch to check. Okay, this is another as well. It's label. Okay, here's loop. Okay, label here. We branch. We check here. So this is where we go. Okay, branch here we go. But here we made a condition. But we already come here. That means what? They're not equal. They're not equal. We come here. We come here. Not equal. What? We continue. We perform our operation. When we continue perform our operation, okay, yeah, then we compare with value of again. Look at those. So this is surely a loop. So this is surely, now let me erase everything here we go. This is surely a loop here. This is surely a loop. So here the loop, inside this loop, okay, mainly we try to add 10 numbers in memory location starting from 100 into the value. Okay, this value is what? Is whatever the value at the memory, which is labeled by SUM. But we load this value into B. That's why at the end we have to save the value. You see, we have saved value back to memory, store to sum. Because we don't know what's the address for SUM. But we can simply using SUM. That's what I showed. That's why, okay, we prefer use label. Okay, like this. So here I showed us all the key components we involved. Okay, initialize the value, that which value we want to add, then also show us the loop counter. Okay, we increment each loop counter, or increment the memory location, so we can add different values, or we compare. Okay, if conditions are met, if we reached our limit, here we go. If we reached our limit, then what? We exit, we branch stop. If not, then we continue. Like this. So this is pretty much a very some information about loops. So for details, I want you guys to read the book by itself. Okay, yes. Then we go to the topic of stacks. For stacks, I remember we have an overview of stacks. Okay, now I mentioned to you guys a long time ago, stack is nothing but a chunk of memory. Or we simply call it what? A stack is a set of memory location, a set of memory locations where data can be stored for what? For short time. This is important. Data stored only temporarily. In other words, we store there for a while, we do something. After we finish, we get back our data. Only to store a memory location for a short time. Now, in general, stack is very useful. When our memory execute a program which has subroutine, or has interrupted service routines involved. So when our program need to call a subroutine, or when our program has interrupted service routine, then in general stack is very commonly used. So why? Because Because when we run a main program, if you need to call subroutine, then we hope to store the values of our key registers somewhere. Why? So we can avoid overwriting the values of key registers during subroutine. So we keep we try to maintain the values of key registers in main program like this. So we talk a little bit more. Same idea when we come to interrupt. So we do something in sequential, our program is interrupted by some high priority events. So we can stop what we're doing now, take care of that. But when you stop here, you should save the key values of registers somewhere. So when you come back, you can use them. Because if you don't save them, then when you go to take care of this high priority events, these key register values may be overwritten by some operation during high priority events. That's called an interrupted service routine. Those. Well, anyway, let's talk a little bit more about the operation of stack. The data in the stack can only be accessed from one end. So that's why a lot of people consider the operation of stack like you're taking a tray in the restaurant. So a stack data structure has a top and a bottom. Has a top and bottom. And a new data can only enter the structure from top of the stack. Like this. So stack we can consider is a memory data structure. Has top and bottom. So we can access data only from the top of stack. But sometimes our stack is empty. In this case, the top and bottom they're together, they're same location. Before we go to the details about operation of stack, I want to refresh your guys' mind about the memory address issue. A long time ago, when we discussed the memory, I always say that assume we have memory at the top. The address for way top location is 0000 in the hexadecimal, and the address for the location at the bottom is FFFF. That's true because for the 688212, which is the main microprocessor produced by Motorola, it assigns a lower address on top and assigns a high address at the bottom. Or we simply call what? The top memory location of what has lowest address, and the bottom memory location has highest address. And I also told you why Intel uses opposite conversion. For Intel, the address of memory location on top has highest address, and the address for memory at the bottom, okay, or the memory location at the bottom memory use what? Use the smallest address, okay. In general, when we power on our 6882 microcontroller, the stack is empty. Okay, in this case, what? Okay, we simply call it the top and the bottom of stack are identical. They are same locations. That's why the address are identical. Because the same location which considered to be the top and also considered to be the bottom. Now, when we enter new values into the stack, then the bottom address remains unchanged. The bottom address is always unchanged, remain the same, while the top address considered to be what? To become smaller. So we simply say that the bottom address remains unchanged, the top address of stack decreases. Of course, if you use Intel machine, then what? Okay, the bottom address can keep unchanged. Okay, the top address won't become smaller, become higher. Now, we said that stack is a set of memory location that was designed for us to store a value. But how the microcontroller can access our stack? So a microcontroller can locate the next available stack memory location to store new data based on using what? Based on the top stack address. Always looking for the top stack address or the top address of stack. That's where it always keeps track of what? Of value, numerical value that we should process. So we call the what? The top address. So the top of stack refers to the address of the last data element loaded into stack. Okay. So how can we do this? How microcontroller can access the last data value we load in the stack? It's very easy using stack pointer, which I mentioned before. Is a CPU register. So CPU or microcontroller using the stack pointer SP, okay, to keep track of the top of stack. Always keep track of it. So when you load a new value, okay, the top address becomes smaller. So the stack pointer, it points to the top one. When you remove some values, or when you take out some values from stack, okay, the top address become what? Become higher. It drop, become higher, and coming down. So okay, so stack pointer is coming down. Always points to the top what? The top of stack. Now, however, at the beginning, where the stack pointer should be. So at the beginning, one should be the value of stack pointer. This is what? Initialized by programmer. Here we go. So the initial value of stack pointer, which is what? Tell us where the top stack should be at the beginning, is determined by a programmer. So here I use memory structure to show you where the stack is and where the top of stack is, and where the stack pointer is. So here I show you. Assume now this is a memory. Yeah, well, assume now that's fine. Here, assume now this is a memory here. This is memory. As I always show you here, this is the top, here we go. This is the top of memory, this is the bottom memory. Okay, look at this. Now we assume this is our memory. Let me choose that. We assume now this is memory. This is stack, excuse me. We assume now this is stack. This is stack. Okay? So this is where, this is what? This is the bottom. This is the bottom stack. Let me use a different color. This is the bottom stack, this is the top stack. So at the beginning, a stack points to here because this is where the programmer specifies right here. Then when we add more value and add more value, here we go. Then what? Okay. The address decrease. That's why when we come to the top stack here, when we come to the top, here we go, address become lower. So if you stop here, when we keep adding new values into memory, into stack, and if you stop here, we go, then this is where stack pointer points to here. So top of stack refers to the address of the last data element loaded onto stack. A stack pointer keeps track of the top stack. Then when we remove some values always from top, okay, like when we go to restaurant, we take trace, always take trace from top. And when we finish, we put back a trace. Okay, then we add more trace like this. So when the person comes to take a tray, always take from top. Now I mentioned what initial address of stack is what is initialized by a programmer. In this case, okay, and so if programmer decide to use a stack to help store some data, then you got to make sure. So you have to leave enough room to grow up in memory. Because if you hope to use what a large number of memory locations as stack, but if the number of locations is too few for you, is not enough, then you get trouble. Now, in general, we can simply say one can initialize the stack pointer to be anywhere in the user RAM or memory. Make sure when we say memory can have ROM or RAM. But because here stack can only be RAM. Stack can only be RAM. Why RAM? Because for stack you can either read data or write data. So it's random access memory. So it has to be the part of RAM, not a ROM. Okay. So in general, as soon as RAM, then what you can initialize. Of course, you cannot initialize memory which is ROM or which is the EEPROM, read-only memory which contains what the machine code, which contains the machine code of instructions. You cannot do that. You can only specify the part of memory in RAM as a stack. Because if it's ROM which contains the machine code for instructions, then you are never allowed to change. So you can only specify what a stack as a part of RAM. Now for the A4, for the 68H12 A4 processor, the optimal choice, for the stack forward, for the initial stack pointer is 800. Why is 800? Because the RAM, the RAM portion for the 68H12 A4 is in this range, from 4000 to 7FFF. So if you initialize your stack pointer at 800, then the first address you can store data is 800. is not 7FFF, not 800. After a while, I will talk a little bit more. Because first address what is only initialized there, it cannot be used. So we simply call what 7FFF is the last available RAM memory location, or is what, or we can simply say it's probably the first memory location that you can store data, but it has last address, but it has what the highest address. So the different microcomputer systems, they have different specification for the range of RAM. But for the A4, which we commonly use, is what start from 400 to 7FFF. In this case, what that's better we initialize 800, the stack pointer address. Now also make sure, okay, the operation for stack data structure is first in, last out. Not FIFO. FIFO is first in, first out. This is first in, last out. Okay, that's what is very similar to the way we take the trace in dining hall to eat. Now let's talk about the instructions. Okay, it's designed for the 68H12 for us. Okay, to access a stack. In other words, what the way we can access data, or we either store data to stack or we take data from stack. So, okay, already designed to use instructions. The 68H12 already have instructions for us to access data using stack. Mainly the two different types of operations designed, or the two different types of instructions, or we call processes, okay, we can use to access data in stack. Push and pull. Push and pull. So push is to place register contents on stack, or we simply call it what? To place the data value on stack. Okay, that's where we need to do that. When we have subroutine, when we call subroutine, or when we are interrupted. Pull is opposite operation. It's place the value in stack location in the register. Now make sure each time when a byte of data, when one byte data is pushed into stack, then make sure stack pointer has to be changed. The stack pointer is adjusted by subtracting 1 from the current value of stack pointer. But make sure we adjust the value of stack pointer before the value is pushed. In other words, we adjust the address first, then we push the value. So this word is very important. This one, highlight this. That's why I said what if you reserve, if you make a stack pointer, if you initialize a stack pointer to be 800, the first address we can use, the first memory location we can use is only a 7FFF. Because we adjust the address first, then we push the value. So if you initialize value is 800, you adjust first. Okay, it decreases by 1, which is 7FFF. Then you store value there. So the location at 800 is not used. So if you push one byte on stack, the address was subtracted by 1. So of course, if you push 2 bytes, assume now we have accumulated D. Okay, we need to push the value of accumulated D on the stack. Then these 2 bytes will take 2 memory locations. Then the value of stack pointer has to be subtracted by 2. This is what I said. Okay, same idea for X and Y, because X, Y contains 2 bytes. But in any way, okay, the new value of stack pointer holds a memory address. of last data byte you pushed on the stack. So anyway, the new value of stack pointer always hold the top of stack, which contains the last data byte we pushed on the stack. So I think pretty much that should be enough for us to come to right here about the access of stack. Then next time we talk a little bit. We talk about specific instructions. We can push data into stack, or we can pull out data from stack. So that's all for today.